Hi, my name is Leandro Facchinetti, and let's write some code together, shall we? What we have on the menu today is exactly what it says on the title of the stream. We're going to try to figure out why pink noise is so slow. Here, let me show you. This is the demonstration effect for the library that we are working together on this stream. It is a library that is going to help you develop real-time audio effects for Reaper. And it comes with a design system with a bunch of colors, and it comes with some things that you would do in audio processing, like having a circular buffer and calculating RMS. Also, it comes with noise generators. We have white noise, we have brown noise, and we have pink noise. So check out what happens when I enable white noise, and I'm going to put a spectrum analyzer on the screen. Now, naturally, you will not hear this because I have everything muted on the master, but check this out. This looks like white noise. There is a slope to this spectrum analyzer. You can turn it off. So now it looks like a straight line. Then brown noise has a slope of 6 dB, descending. Great. And then there's pink noise. And I'm barely producing a sample every second. And as far as we know, it is pink noise. We do a track with pink noise and was okay. I mean, the technique that we are using to generate is not necessarily the best technique in terms of performance. And when I say performance, it means it's not exactly a 6 dB slope as it should be. But it's good enough. There are some bumps. But what is really bad is that we are consuming 160% of the CPU to generate this pink noise. That's why we are not able to produce as many samples as we need, and the audio is dropping out. Why is that happening? I think that the implementation is correct. It's just absolutely annoyingly slow. So why would that be? We'll figure it out together, hopefully. Maybe. We'll see. So let's jump into the part of the code that is actually implementing white noise. And Bo is here. Hi, Bo. Great to have you here. I hope you enjoyed this. It's going to be an investigation of why this thing is slow. Enjoy the ride. So let's review the implementation of pink noise, because maybe there is a bug somewhere. And maybe it's slow because of a bug. And then we are going to think of things that could be slow, measure, we'll see. So let's go over the implementation of pink noise again. So the idea that we are implementing, there are many different ways to get pink noise. Bo has a question. I was going to say that audio was really weird, but it seems to be fixed. Was it the heavy CPU usage? Probably. That's why I turned it off. We're back to white noise. So yeah, probably it was just consuming so much CPU that there was not enough CPU for the stream. Right, so there are many ways of getting pink noise. The way that we are implementing in particular is based on this paper or this article that was published in Scientific American in 1977. The idea is just that we have 6 different sources of white noise, and we update these generators, these sources of white noise, at different rates. And one of them is always updating. For every sample of pink noise you want to generate, you generate one of these white noise sources. But the other 5, they are updated only every other sample, every 4th sample, every 8th sample, every 16th sample, and every 32nd sample. And if you add this all these generators of white noise, they are contributing different parts of the spectrum. If you only update a source of white noise every other sample, it's essentially a low-pass filter that you are applying to the source of white noise. So it's contributing more to the lower frequencies than to the higher frequencies. And if you add up all of this, you end up with this series. It's actually a series of bumps but it's close enough to a straight line with a 6 dB, with a 3 dB slope. So this number here is controlling the number of sources of white noise, and we currently have 5. And as far as I know, 5 is good enough to get good pink noise right slope for the spectrum of frequencies that we can hear. But we can play around with this number, because maybe if we have fewer sources of white noise, the performance gets a little better, and that could be a clue. So I guess I'm going to start taking notes. I'll leave a to-do here. Check if decreasing the number of white noises helps. Then pink noise has to, this generator of pink noise has to remember previous outputs. So we have a data structure for that. And it is remembering all the sources of white noise. That's one of the fields. Then we have a counter because we need to determine which source of white noise to update. And then we have a sum, which is just the sum of all the white noises. And this was supposed to make things faster. Now, this thing is so slow that it is funny for me to bring up something that was supposed to make things fast. But the idea of this sum is that I don't have to keep, for every sample, re-adding all the elements in the white noises array, because there will be only one that is going to change each time. So it doesn't really make sense for me to add all 5 of them together. Makes a lot more sense for me to carry the sum, then I subtract the old sample and add the new sample when I'm updating the white noises. Now, to actually instantiate this data structure, so this is the definition of the data structure, and this is an instantiation of the data structure. I just create this local variable noise, then I allocate. That doesn't seem right, does it? Oh no, it is right. So I just allocate a chunk of memory with 5 slots for my generators of white noise. Then I start the counter at 0 and I start the sum at 0. All that makes sense. So I'm just initializing these fields in the data structure. Then to actually generate a sample of white noise, I'm going to have to first deconstruct this noise is an instance of this data structure. I'll have to deconstruct that to get a hold of the white noises, the counter, the sum. And then this index is just going to be the place that I have to update the white noise generator that I want to update this time. And then the implementation goes like this. First, I fetch all these things, the white noise source, counter, and sum. And then at the end, I'm going to store the updated values. So this doesn't seem right. No, it is right. So this is an array of white noises, and I'm going into the index that I want to update, and I put my generated sample there. And I will have changed the counter and the sum, so I save them for next time. And the bulk of the work is to generate a new white sample that is going to be stored in this array, but it's also going to be added to the sum. Then, to determine which generator to update, hang on, I'll be right. Okay, I'm back, 35 sneezes later. So to determine which generator, which source of white noise I need to update, I am going to count the number of leading zeros in this counter, which is kind of a crazy thing to do. In fact, it's such a crazy thing to do that I'm going to leave a to-do here, which is already a to-do somewhere else. Extract and test this function that counts the number of leading zeros. And I want to extract and test this because there may be a bug here that may be the culprit of this whole thing. So we start at 0, then we are checking the counter, which is just a simple counter. I'm just going from 0 to 1 to 2 and so forth. And I'm looking at this number in binary, and I'm checking, I'm doing a bit shift of 1 to the left by the amount given by index. So I'm starting by checking the 0th position, counting from the right. And I bitwise AND these things, check if it's equal to 0. Because if it is equal to 0, then that bit was 0. So I go to the left once more. And I will also leave a to-do here. Is it the conversion from floating point is like this, right? To binary, sort of making things slow, because in JS effects all variables are floating point numbers. So this counter and the index and everything, they are all floating points underneath, and I'm using them as integers. I'm using them as essentially bit strings. So maybe this conversion could take a while. I don't know. We could check this. And another possibility is actually up here. To do is the issue that we are going to memory too often. I really don't want this to be the case, but we are using a lot of memory access to do this, so maybe it's too much. Now, it is about the same number of memory accesses that we have on things like filters, so it shouldn't be an issue. But if this is the culprit, if this is the reason why things are slow, then maybe this whole strategy that I'm proposing for the library will not fly. That could be said. Right. So then to actually update the sum, I subtract the previous version of the white noise generator. So I take it out of the sum and I add the new version. I increment the counter. I check if the counter is equal to a particular number that I think I devised this experimentally because looking at this, I cannot really understand everything that this thing is doing. But the point of this expression is just to see if the counter, if we did a whole cycle of updating the white noise sources. If we did, then we reset the counter. And then, yeah, this I already explained. So now we have some things to test. I am going to start with this. Not necessarily because I think this is not necessarily because I think that this is the thing to blame, but because I think that extracting this is useful. It may be something that you may want to do in other situations. So in fact, with this refactoring, I'm going to see if there is a bug, but also I'm probably going to make things even slower. Because if there is no bug, then there will be a function call here, and a function call will slow things down. So I'm gonna start investigating a performance problem by making it worse. Let's define a function in the beginning here where we have some mathematical functions. And I'm gonna put it here. Numerical functions. Leading zeros. Count leading zeros. Is it leading or trailing zeros? Now I have to think about this. I am going to consult Google. Leading zero and trailing zero. I think it's trailing zeros. Yes, okay, these are the trailing zeros. Yeah, okay, it's the number of trailing zeros. Of a particular number. I will need a local variable that is trailing zeros. And then I will do this logic. And return the number of trailing zeros. Naturally, the counter here is going to be the number that I'm checking. And this is going to be the trailing zeros. Now let's find our tests. And we are right below arc. Blah, blah, blah stuff. But we are before distance. So this is the right place to add this test. And then I create a test for this. In which I call the number of trailing zeros of 0 and 1. So in zero, actually, the number of trailing zeros is infinitely many. I think we found our bugs. This is going to be super slow, right? Because it's going to go all the way to the left. I wonder what the function just does right now as it is implemented, because this is if not a bug, it's something very expensive to do, because if the number is 0, then it's going to keep going to the left, trying to find that first one, and it may never reach that. So that is, it was supposed to loop forever, but it doesn't. So that is weird, isn't it? Let's load. I have a test effect that sometimes I use for things like this. You can see there is even a syntax error in there. It doesn't really matter. It's mostly junk. So I'll copy and paste this function there. And let's experiment with this. So if I ask for the number of trailing zeros in 1, I get 0. That is the correct answer. And for the number 2 is represented in binary with this pattern. So it was supposed to give me, as a result, the number 1. And it does. Then for the number 3, I'm going to start writing the tests for this, right? Since I'm reasoning about these things. I think I'm going to go up to 8. And I think I want to put comments here of what these numbers actually are in binary to help the reader along. And I will need 3 digits, actually 4. And then it's relatively straightforward for me to see the number of trailing zeros. In this one, there is 0 trailing zeros. In this one, there is 1, 0, 2, 0, 1, 0, 3. So now you can see that because of the way we are employing this function, you can see that we are going to update the 0th position every other sample, or the 0th white noise generator. I'm going to update it every other sample. The first 0th first, right? So the first white noise generator is going to be updated every 4th sample. 1, 2, 3, 4. And then we are going to update this guy every 8th sample. I don't have enough tests to show this, but I think that this is correct. And to check, we can always go to this link where there is a cute little diagram showing which source of white noise should be updated for every sample. The pattern is supposed to look like this. So let's see, this I'm gonna call the 0th source of white noise, and it's updating every other sample like this. Great. So the pattern goes like, how about I just copy and paste this over? And this is source 0, this is source 1, this is source 2, and 3, and 4. And it's supposed to go like this. So it goes 0, 1, 0, 2, 0, 1, 0, 3. Yeah, this pattern looks correct. The only glitch is that I should not be calling it with 0, because the number of trailing zeros in the number 0 is infinitely many. So the real trick here is, well, it's easy. I just have to start with 1 instead of starting with 0. Classical off by 1 mistake. But I wonder what is happening if I just call it with 0. So let's go back to our experiment. And first, I want to quickly verify that these values are going to do the right thing. So can I do it like this? And get this out of the way. Then we can experiment. So one evaluates to 0, and 2 evaluates to 1. All of that seems to be right. So this function really is working, but what happens if I call it with 0? That is a huge number. And this huge number is going to be somewhere in memory that is absolutely unrelated. So this is going to be something crazy. This is no good. And what is this number? I really don't know. It is weird. I don't think this relates to the number of digits on a floating point. It's just a weird number. This is no good, right? Because I'm I am going to the left this many times trying to find this value. And of course, this is relatively fast when I just try to peek at the value. I hit Command Q and I immediately see the answer. But when I'm doing that on every sample, that cannot be cheap. Cannot be cheap. So I'm just going to say that you're not supposed to call this function with a 0. And usually I would put some kind of error checking, but we are trying to avoid error checking because the error check takes time. So I would need to put an if sort of situation here. If the number is equal to 0, then return an error. Otherwise, compute the number of trailing zeros. So I would copy and paste this like that. But I don't want to do all of this because this check is already something that is expensive. So I'm just going to say by contract, you are supposed to not call this function with a 0. Great. So now let's run our tests. Sure, you can save that. Take out the effect and drop in the effect again. Now this thing is not syntactically correct. It's complaining about line 147. Oh yeah, this is not syntactically correct, is it? I'm gonna put this in a temporary buffer. Try again. And then let's go to the page that runs the tests, and our tests for count trailing zeros is passing. But I am missing this to make the test look nice. Right, so this is part of the investigation that is getting me something. I'm happy. I'm going to commit. But there is more. We need to check the boundaries of the counter. First, let me employ this function where it needs to be used. So down here where we are counting the number of trailing zeros, I'm going to remove this because I already did it. And I want to count the number of trailing zeros in the counter. And that is going to be my index. And then I can get rid of all of that. And then let's think about the range in which the counter is supposed to be. Now, note how this pattern repeats. This second half here is the same as the first half, so I don't need a special case for that. Once I get up to 4, I can reset the counter. Let's draw some good-looking table here. Oh no, I will run out of digits. That's all right. You can have something like this. Right? Not the best, but it looks okay. So I actually don't want the numbers to go on this range. I want them to go like this. So I want them to go from 1 to 16 and then wrap back. So in my counter situation here, I started at 0. That's incorrect. It should start at 1. And I am adding 1. That's all right. And when I want to wrap back, I should wrap back to 1. And what is this number 16? Well, I have 5 sources of white noise going from 0 to 4. So I have 5 sources. And 16 is equal to 2 to the power of 4. Am I right? I don't know. Am I right? I don't trust myself anymore. Yes. So I suppose that this is 2 to the power of number of white noises minus 1, right? 5 minus 1. So that's what this number is. Oh, but it's not only that. I don't want to wrap back on 16. I want 16 to be able to occur. And if I am wrapping that back on 16, I'm not allowing 16 to occur. Because the next time we go around, it's already going to be 1. So I want 16 to occur. So I guess I can do it like this. If it is equal to, and the number of white noises is this, minus 1 plus 1. I wonder if there is a better way of writing this using bit shifting and that sort of thing. And another thing is every sample I'm computing this, but this is something that is only related to this constant. So I think I can pre-compute it. I think I should pre-compute it. And I'm going to say that this is the white noises counter maximum. And then I don't really have to worry about making things fast. It's not really a maximum, it's one more than the maximum. So what if I don't add 1 and I check for greater than? Okay, I think that now the logic holds water. Let's quickly review this and then we can try it out. So let's say that, for instance, for this guy, we want this maximum to be 16, and we are talking about 2 to the power of 4. That is all right. Then on this one, it's going to start at 1, and this is also going to start at 1. And if the thing is, it is going to go from 1 up to 16. And if it's greater than 16, when it gets to 17, it wraps back to 1. That seems correct. Great. Now, place your bets. Do you think that pink noise is going to be fast now? What do you think? Fast or slow? Place your bets. Do you think that was the bug or the only bug? Oh, look at this. Not bad, huh? The CPU is perfectly all right. And we are generating some noise. Is it pink noise? To check that, we need a slope of 3 dB. The thing was supposed to be relatively flat. Now, it is relatively flat on this region. There are definitely some dips. We can see a little bit of comb filtering, but down here, it is very bad. It's not a 3 dB slope in this region. It is not, sir. but at least it is fast. So there you go, it was a bug after all. Now, let's go over the to-dos again, because some of them may have fallen out of scope. I do want to play with the number of white noises. It may even affect the quality of the pink noise. Then, is the issue that we are going to memory too often? Probably not, because we are doing the same with filters and the CPU is fine now. It's not awesome. It's not great that I'm consuming 0.2% of the CPU to generate pink noise. It's not awesome, but we know that generally the performance of our library is not going to be the best, I don't think. Is it the conversion from floating point to binary that is making things slow? Maybe. Maybe it is. But I'm not sure if I can do anything better, because the only thing that comes to mind is I could get my number and do something like this, which forces a conversion into a bit string representation. But I think that, and you do see this in some plugins when they want to interpret a number as an integer. The problem is, if I do it like this, I don't think that like my AND in the implementation of count trailing zeros, I have an AND with something else. I think that this is going to force the thing into a number, into a binary string just the same. So maybe if but the counter is always changing. Yeah, so maybe if I had something like this, the performance could tangentially improve, but I don't think it will. But we can try. Yeah, let's try. So right now it's taking 0.2, 0.1%, sometimes 0.3% of the CPU. If I do something like this, I am forcing this counter to always be... This is voodoo. This really is voodoo. I don't think it's going to make any difference at all, but we'll try. Yeah, there is no way for me to force things into being integers. It's just the nature of the game. And so the only thing left is to play with the number of white noise sources. I think I'm going to have a slider for this real quick. I'm committing because I will probably want to change this in the near future, or I'm probably not going to keep the changes that I'm making, but let's have a slider 15 called remove me that starts at 5. And no, I cannot do this because it's going to affect memory allocation, so I cannot just have it in a slider. No, the only way for me to test this is to come here, change the number in here, and then look at it. So reload the whole plugin. All right, so let's have a before kind of thing. So we have a slope of 3 dB. And this is with... Can I have a text box? Thanks. This is with 5 sources of white noise. Then now we have how many? 4? 4 sources of white noise. I think that the comb is a little bit better, but this slope is even worse. Yeah, I think that this is the case. Four sources of white noise gives me this. Oh, come on. Help me out here. Can you please show the number? Thanks. Then 4 didn't make us happy. How about 6? This is better. This slope is decent. It's getting better. Now, naturally, it's going to make things slower as well, so we have to watch the CPU usage. Let's go to 10. The CPU is about the same, which I guess makes sense. I was thinking that the more we had, the worse. But it's not like that. It's just a little bit more of memory use. But yeah, it's just a little bit more memory that is being used. But I'm only updating one at a time. So I guess the counting of the trailing zeros is going to be slightly slower, but not by much. And then is the response going to be better? And the answer is yes. The response is super flat now. That makes me happy. We are about the same in terms of CPU. The response here looks super flat. The comb is almost gone. There is only 2 dips that I can count. Yeah, I'm happy. I'm going to go with 10. 10 is our number. And it is not straightforward to change this definition. You cannot change it at runtime. You cannot have like a slider for this. So this is a magic number that we are calibrating, and the library is just going to ship with this hard-coded. I'm going to note that this was calibrated by hand while looking at a spectrum analyzer with a 3 dB slope. And yeah, I think that this was all fun and games, but I don't think I need to keep this around. So I can delete this buffer. And that was a success. We fixed the performance issue. Great. How about we take the last moments to implement the biquad SVF that we left off yesterday, because I didn't finish implementing this. So how about we just take this last 10 minutes to do that? And there are some clever comments. In fact, I want to shout out to Justin Johnson, the developer of REQ. He watched the stream yesterday and sent me an email with very smart comments. And I'm going to go over them. I was thinking about doing it at some other point because I was thinking of checking with him that it was okay for me to share that, but I think it is okay. So yeah, let's go over his comments, and then we implement the rest of the formulas. So I'm not going to show his email on the screen. I didn't ask his permission to do that. But these are the things that he mentioned. First, it's a naming thing. He says that an SVF filter is not a biquad. The RBJ cookbook filters are biquads, and the SVF is not a biquad. That's what he says. I'm not so sure about this. I think that the jury is still out on this one, because he mentions that the derivation of the formula is different. It's using that trapezoidal thing, trapezoidal integration. But I think that is just a way of arriving at the coefficients and the formulas, but I do think that the nature of the filter itself is the same. That's why the SVF filter and the RBJ filter have the same shape. In fact, how about we play around with this? I don't think I did that on the stream yet. So let's drop a demonstration effect and let's drop the EQ curve analyzer on the track. And I want two of these demonstration effects. One is going to be the RBJ filter, and I actually want to do something that I don't think I did before, which is to have some peaking EQ and show the warping that happens near Nyquist. See that? How the shape starts being asymmetrical near Nyquist. And this is only showing up to 20 kilohertz, so can only go up to this, which is kind of weird because my sample rate is 48K. I was supposed to go up, I was supposed to be able to go up to 24K here, but I'm not, just because of the way that this Burton EQ curve analyzer works. But in any case, so we cannot really see it getting back to zero, but it will get back to zero at 24K. And that's why it has to cramp near Nyquist. It has to distort there. Now, I wanted to have two of them because I want to be able to get in here and switch to an SVF filter, ATM machine. So I want to be able to go to SVF, and I only have a low pass at this point. That's the only one I implemented. But the case that I want to make is if I have both of these, just one for now, and I have a low pass with a Q of whatever at 1,000, not 100, 1,000. There. So if I switch between the two, look at the shape. I think it moves 1 pixel to the side. It is the same shape. So these filters are the same filters. And when we implement the SVF for peak, we can show even the cramping near Nyquist is supposed to be the same. The only difference between the two is numerical stability, the fact that you can interpolate between coefficients using SVF, and if you tried to do that with the RBJ formulas, your filter would be unstable in between points. So in essence, they're the same filters. So I think you would classify, if you say that RBJ filters are biquads, I think that SVFs would be biquads as well. The number of poles and zeros in a pole zero diagram is the same, I think, because they're essentially the same filter, just implemented using different formulas for when you get to the real world of computers and how they truncate numbers. It's going to work out. But there is more. Justin also says that the M0, M1, and M2 coefficients, let's find them. So we are computing them here, for instance. And these are mixers. That's why they are M1, M0, and M2. They are mixers where they're mixing high pass, band pass, and low pass. So check this out. Then I think it's even in order. I think I wrote this in order. So high pass, band pass, and low pass. No wonder the low pass filter has 0 and 0 as the first two coefficients, because you don't want any high pass, you don't want any band pass, you just want the low pass. So this tails back to the thing I mentioned yesterday, that the SVF thing is one circuit that implements all kinds of filters. It's a universal filter. So you just have to say which parts of the wires you want to tap into, and you will get different results. And then you can combine low pass, high pass, and band pass to do all the other kinds of filters, like a high shelf. If you want to boost with a high shelf, you can just have an all pass. So you're going to have a wire that just gives you directly the input, and you can add a bunch of some high pass, and you will end up with a high shelf, for instance. So that's the kind of thing you can do. And in other words, you can construct all kinds of filters just by mixing these three kinds of filters, and then you have to mix them in a smart way. And the B zeros, A zeros, and whatnot in the RBJ cookbook, they are directly the coefficients that you would use in direct form 1 when using biquads. So there is no direct correspondence to between coefficients and the outputs. They're just magic numbers essentially. While here with the mixer situation, there is a bit of a correspondence between these amps and what you see in the output, which is great. And he's talking about also the REEQ implementation. I mentioned yesterday how he has a tilt EQ in REEQ. Let me show that again. So there is all the usual suspects, and then there are these ones that are kind of special at the end, like a tilt shelf. And this, I mentioned, is just a combination of a high shelf and a low shelf, and they are controlled with a single knob. But they are essentially just the filters that we have implemented, put to use in a smart way. And there are only two exceptions here. The low cut or high pass with a slope of 6 dB, that is not using SVF. And as far as I understand, that's because that is a single pole, not a two pole. So it's not a biquad. This one is not a biquad. It's a single pole kind of filter. That's the kind of filter that we are using in Brownian noise, by the way. The Brownian noise generator pretty much amounts to a low pass or a high cut of 6 dB with about here. So the slope starts about here, and then there is this 6 dB slope going down. So that's essentially what we're doing for brown noise. And our brown noise generator, as I pointed out in previous episodes, it's pretty much a single pole first order low pass filter. So this implementation is not an SVF. But then the 12 version is the SVF one. And if you want to go to 24 or 36 or 72, you just add or cascade more of these filters. You put two of them in a row, you get 24. You put them three of them in a row, you get 36. And if you want to get to 18, you put a 12 one cascading with a 6 dB one, a single pole one, and you get 18. So that's how you can do all these shapes. And yeah, what else? Even the Butterworth filters have been implemented with SVF, as far as I understand. You just have to pick right settings for Q, and you will get a flat surface over here, no ripple on the passband, and that's a Butterworth. And you just have to be careful about picking Q. That's why you cannot really select a different Q for the Butterworth filter. So it's also done with SVF. And even other things like the Poltec low shelf, also just a combination of some SVFs. A low shelf with a with a bell here, with a peak over here. And what else? So we should store these intermediary values G and K if we want to draw the frequency response. So if we want to be able to draw this diagram, we need to store those values. They're going to be necessary. And also something that is super helpful to know, if you want to morph between this, if you want to go from low pass to high pass, which is something that you can do in the auto filter in Ableton, which is fun. So you can morph a filter into another. You can do that by just linearly interpolating these coefficients, which is amazing. And if you want to like move the cutoff frequency of the low pass filter, you can also just interpolate. Yeah. So thank you very much, Justin, for all the insightful comments and for watching the stream. I hope I made justice to your email, and I hope you agree with me just sharing this on the stream. So let's implement the rest of the formulas and get out of here. In particular, I want to compare, let me put some to-dos here. I want to compare RBJ and SVF in terms of warping near Nyquist. And I want to see the difference between peak and bell, which is, as far as I understanding, REQ, there is only peak, there is no bell, and I wonder why. So I want to see this using the curve analyzer. So let's get to work. I'm actually going to prioritize the ones that I want to look at. So peak, because I want to see the cramping, and bell. So I'm going to start with peak. Is G always the same? It looks like in all these formulas G is the same, so I might as well just pull it out. And K is always the same too. And not only they are always the same, but they are always necessary. G and K. No, it's not the same here. Because you have to multiply by the gain. Yeah, let's not. So I'll just copy and paste this over. That's fine. So I was doing peak. And cutoff is called frequency and sample rate is called as rate. Q is called Q. Okay, let's double check. And let's go to bell. For bell, I also need a capital A, so I don't think I have that as a local variable. Let me go ahead and define that as a local variable. And this bell gain dB is called just gain. I like how I see lots of similarities between this formula. Seems like there is something powerful underneath when you see that kind of order. Right, let's review this. Looks correct to me. So unfortunately, I hard-coded the demonstration of this. So instead of a low pass, I will have a peak at the peak is not using the gain? What the hell? I don't think that peak is what I think it is. Because where is the gain here? Am I right? That is weird. But yeah, as far as I can tell, the gain is only used in the bell shape. That's gonna be interesting. And the Q is always used, so that's all right. Now we're gonna have a peak filter. Let's drop the effect into the track and look at it. Huh. This is a peak, but I cannot control that peak gain. How about the bell? So Bo explained yesterday that the bell is just going to it's going to be similar to a peak, but it's going to have a flatter top. Let's put a 6 dB gain there. And let's see that in action. Yeah, I must be honest, I don't think I see anything flatter. I see the same overall shape. I do see that with this one I have a gain knob that I can play with. So that's always nice. Now, let's bring this up and closer to Nyquist. Let's see the warping. So right now I am using a low pass. Let's use a peak. And with this formula, we do have control over the gain. And let's go to somewhere where the cramping is obvious. So maybe over here at 12,000. You can definitely see the shape starting there. We can go further probably. At 15, it should be pretty obvious that there is an asymmetry here. And let's reproduce this by hard coding these values into the SVF filter. So we will have a bell at what? 15,000, and the gain is 6, and that is our Q. And then we reload the effect on this one. No. Okay. So this is the SVF filter, and this is the RBJ filter. Let's alternate between the two real quick. I don't see any difference in the response curve. So we are proving that, yes, the SVF filter really has the same shape as the RBJ filters. It boils down to numerical stability and extra nice features like interpolation for morphing between filters, but it's just that. It's nothing magical that is going to solve all your problems. But at least one problem we solved. Pink noise. Great. See you tomorrow over here for some composition with Arya, hopefully. Maybe. We'll see if he is feeling better. But if he is, we'll be over here writing a duet for cellos and flute. And on Thursday, I will be back to the JSFX library. Thank you all for being here, and I see you tomorrow. Bye.